Welcome to Unit 8 on gases. This is Lesson 3, video number 1. So we're going to look at another gas law here, and this is Charles' law. And Charles' law was discovered by Jacques Charles in 1787, and he studied the relationship between the volume and temperature of a gas, and pressure and moles are held constant. And he found that the volume of a gas over its temperature is a constant. So with this, V over T is equal to a constant. We're not going to go over the derivation of this, but in this case, temperature must be in Kelvin for all of these equations. So V1 over T1 is equal to V2 over T2. This means that as volume increases, temperature has to increase in order for this constant to be the same. So that gives us these: a temperature increases, volume increases, because the gas molecules are moving a little bit faster. That means that these are directly proportional. And if we looked at a graph of volume versus temperature, it would be a straight line with the slope equal to this constant. So the rationale for Charles' law is if we increase the temperature, we know that that increases the speed of the molecules. That increases the number of collisions. That in turn would increase pressure, but in order to hold pressure constant, we had to increase the volume to counteract. So the volume has to be increased because the pressure is causing that to expand out. So for all of these example problems, we're going to use the equation V1 over T1 is equal to V2 over T2. So this is the original, and these are the new conditions. T must be in Kelvin, and volume units must match. So if one thing is in liters and the other's in milliliters, we have to change one. So let's look at our first example problem here in the next video. Actually, we'll just look at it in this video. So a sample of nitrogen gas occupies a volume of 520.0 milliliters at 150.0 Celsius. What is the volume of the nitrogen if the temperature increases to 548 Kelvin if pressure is held constant? So, like we did for Boyle's law, we're going to do our variables, V1 and T1, V2 and T2. So our first volume is 520.0 milliliters, and that is at 150.0 Celsius. We know that that temperature has to be in Kelvin, so we have to add 273 to that number to give us 423.0 Kelvin. We want to know what the new volume is if the temperature goes up to 548 Kelvin. So now we put these values into our equation. V1 over T1 is equal to V2 over T2. So to solve this one, I'm going to multiply both sides by 548 Kelvin. That gets rid of this and leaves V2 by itself. So I take 548, our kelvins cross out, 548 times 520 divided by 423. Now you could cross multiply and get rid of the fractions, but we don't have to. 548 times 520.0 equals, divided by 423.0 equals. And there is our answer. Now we have to look at significant figures. Look at the values given in the problem. This one has 4, 4, 3. So we always go with the least number. So 673.6643026 rounds to 674 milliliters. So the temperature went up, the volume went up, and that is what happens with Charles' law. When one thing goes up, the other one goes up. They're directly related. Let's look at example number 2. Here we have a sample of water vapor with a volume of 84.5 liters at 600 Kelvin. So here is our volume and our temperature. At what temperature in degrees Celsius would the volume be 75.2 liters? So volume 1, temperature 1, volume 2, temperature 2. Volume number 1 is 84.5 liters. Volume 2 is 75.2 liters. So the volume is going down. So if our original temperature is 600 Kelvin, we want to know what our new temperature is. But we want that in degrees Celsius. So we're going to have to solve for Kelvin first and then change it to Celsius. So V1, 84.5 liters over T1, 600 Kelvin, is equal to V2 over T2. So for this one, it might be easier to cross multiply. So 84.5 liters times T2 is equal to 600 Kelvin times 75.2 liters. Then we can divide both sides by 84.5 liters. That crosses that out and gives us T2. So we would take 600 times 75.2 divided by 84.5, and that gives us this answer. But we need 3 significant figures, so 534 Kelvin. But we want it to be in degrees Celsius, so we have to subtract 273 from that. So 534 minus 273 gives me 261 degrees Celsius. And there is my answer.